All right, we're moving on to our next session featuring Dr. Jesús Barrasa and Mark Needham. Please don't hesitate to ask questions using the questions tab on your screen. We'll have a brief Q&A session at the end of the presentation. And now here's Lance Walter to introduce Jesús and Mark.
Dr. Jesús Barrasa has been with Neo4j for 5 years in consulting and industry solutions roles. Dr. Barrasa has a master's degree in software engineering from ENST Paris and a PhD in AI and knowledge representation from Universidad Politécnica de Madrid. Mark Needham is a 7-year Neo4j vet and works as an engineer on our developer relations team. He is widely known and loved by our community for his technical expertise and just being a terrific person to spend time with, and also a great advocate for graphs. Mark spent his pre-Neo4j career in software development roles, and he's got a bachelor's degree in computer science from the University of Warwick. He's also the co-author with Amy Hodler on that popular O'Reilly Graph Algorithms book. You know, the connection between graphs and ontologies is very well established, and it's important to understand. And natural language processing is popping up more and more in the context of AI and graphs. So I think we've got a great session to have here. Welcome, Jesús and Mark.
Thank you, Lance. It's great to be here again, and great to be doing another talk with you, Mark. It's been a while since we did last in that online meetup.
Yeah, so, we've got the gang back together again.
Exactly. Right. So today we're going to be talking about how to build a knowledge graph in Neo4j, but we're going to approach it from a particular angle, which is we're going to combine public resources in the form of taxonomies, ontologies, and then combine them with unstructured documents where we're going to do NLP on, and we'll see how combining the two bring a pretty powerful combination of elements to build a knowledge graph in Neo4j. So that's the plan for today. And I'm going to start with a very brief introduction of two main elements, and I've kind of already introduced them, that we think are key in a knowledge graph. So of course you need some data, you need some facts, you need some information, you need to build a graph. But then in addition to that, we're going to want to have also what we call explicit knowledge. We want to add additional information on the elements that describe your data. Just to give you an example, I mean, if we're talking like we're going to be about articles, you can organize articles by the topics they're about, and then these topics can be subsequently organized in, for example, hierarchies, in taxonomies, or they can be related in many other ways. So this idea of combining defining the structure of the elements in your data, in your graph, is what we call explicit knowledge. It's also referred to as ontologies. That's kind of an informal definition of what's understood by an ontology, which is a definition of a domain in terms of the terms and relationships between them. And just to also to align it to what you probably will be familiar with in Neo4j, well, facts is the data that you naturally or typically import through load CSV that will come from relational sources, from tabular data. It can come from streams of data like JSON, etc. So the typical data that will form your graph. But then the explicit knowledge will be something that you either build yourself, if it's your enterprise ontology. It can be your own taxonomy, your own organization of your metadata, so referred to as sometimes, or we can also bring it from public resources, and we're going to be using Wikidata today for that. So in our software knowledge graph, which is the demo that we're going to be covering in the second part of the session today, we're going to be taking the taxonomy of software information, because we're going to be working on articles from Dev2. So we're going to be picking a set of articles from that website. We're going to be structuring them using NLP, taking out the entities that are mentioned in the text, and then linking them to this taxonomy that we'll get from Wikidata. We'll take different aspects, and we'll show how to do it. And finally, we'll add our own manually created ontology in OWL. So these are the 4 elements in the software knowledge graph that we'll be building today. So now I described the what, but then the question is why? Why do we want to build a knowledge graph, and what kind of things can we do? What kind of problems do we solve? So one of the things that we're going to be able to do is enhance our search, do what's called sometimes semantic search. So not search for terms, which is sometimes a powerful way of exploring your data, but also expanding it to concepts. So if you're looking for documents about a particular topic, you want to maybe be presented with articles about related topics or topics that are more specific versions of the one that you're interested in. So this idea of exploring the concept, the semantics of what you're asking for is what we're going to be, is one of the reasons why you want to build this kind of knowledge graphs. Semantic search is one. A second possibility is something quite similar, which also explores this idea of similarity or relationship in the graph, which is provide like similar documents, provide recommendations, provide customizations. So doing concept similarity is another thing that we'll be able to solve, and we'll show some examples of that today. And then there's two other aspects that we will not be covering today, which is inference and for example, inconsistency detection. Depending on how rich, how expressive your explicit knowledge is, the ontology part, you will be able to do more or less things. And if you bring additional elements in your ontology, things like we've mentioned hierarchical relationships, but you can also bring domain and range relationship, disjointness relationships, then you will be able to do more advanced, more sophisticated inferencing. And the notion of detecting inconsistencies is similar, kind of is a way of, rather than deriving new knowledge, which is the idea of inferencing, is detecting information that contradicts the knowledge that you made explicit in your ontology. A simple example would be, I've defined two entities or two concepts as disjoint, as incompatible between each other, but then we happen to have documents or entities or instance data connected to both. Well, that's kind of a contradiction. So these sort of things you will be able to detect as well. Probably will not cover that today. We'll focus on the first two, but that's the plan for today. So Mark, maybe you can continue with the tools that we're going to be using.
Yeah, so we're going to be using three tools, so you can see here. So we're going to, as Jesus was saying, we're going to be using the Wikidata. We're going to be using Wikidata. So we're going to pull in some data using their Sparkle API. We're then going to use a tool called Neosemantics to get it into Neo4j. And then we'll finally be using a tool called APOC to do the NLP part of the talk. So we'll just break those down one by one. So Wikidata is the sort of the place where the structured data of Wikipedia is stored. So more or less, if you can find a Wikipedia page, then there should be a Wikidata entity available for it. So you get one page, you get one entity. Neosemantics, or you'll often see it called N10S, is a plugin that enables you to use RDF in Neo4j. So this is a tool that's created by Jesus. So it allows you to store RDF data in Neo4j, or equally you can take data that's already in Neo4j and expose it out as RDF. And then you can also do constraint validation and inferencing, as we talked about a couple of slides ago. Next, we've got APOC. So this is Neo4j's standard utility library. So it has between 450 and 500 procedures and functions for doing all sorts of different things. Since Neo4j 4.1.1, it ships with Neo4j, but you can also download it if you want to. And then the particular part of it that we're going to look at today is the natural language processing procedure. So these are wrappers around different cloud APIs. And in particular, we're going to look at the Google Cloud Platform ones. So the rest of the talk is going to be a demo. And so this is the structure so that you can keep a rough idea of where we're up to. So we're going to start by looking at Wikidata. We'll import that into Neo4j. Then we'll scrape some technical articles from a developer website called Dev2, but we'll explain that if you've not seen it when we get there. Then we're going to use entity extraction using the GCP NLP API, and then finally we're going to learn how the types of queries that the combination of these two techniques enables. And so if we just loop it back to that first slide that Jesus showed with the facts and the explicit knowledge, the Wikidata taxonomy or ontology is the explicit knowledge. The facts in this domain are the technical articles we're going to scrape from Dev2, so it'll be like the title of the page with the contents of the page. And then the entity extraction connects those two graphs together. So what we're going to do now is we're going to switch over to the Neo4j browser, which is a tool that you can use to run queries against Neo4j. And we're going to go through a browser guide, which will show us how to actually combine all these techniques together.
Okay, give me 1 second and I'll start sharing my screen. Let me know when you can see it. So that's hopefully in front of you now. So you should see, let me know, Mark, when it's...
Yeah, so you can see it now. So you can see that we're playing the NLP_knowledge_graphs guide. And if you want to play that yourself, you can do it with exactly the same command as we've done there. So I'll let Jesus talk us through the first bit now.
Great, thank you. Yeah, so we have the guide that's going to take us to through the different steps of the demonstration. So yeah, first you'll see a couple of links to the two main components that we'll be using. The first one is NTNS, Neo-Semantics, and like Mark said, we're going to be importing data from Wikidata. Well, not data, the structure, what we call the explicit knowledge, the taxonomies, the software taxonomies from Wikidata. So we're going to use Wikidata API. So Wikidata stores data as RDF and offers a Sparkle endpoint. Sparkle is the query language for RDF. So what you see in front of you now, it's a Sparkle query. I won't spend too much time in the details of it, but if you focus on the where part, that can give you a little idea of what we're doing. So everything in Wikidata is identified by these alphanumeric codes. So it might be a bit arcane if you're not familiar with them. But the good thing is that these query endpoints gives you the opportunity when you pass the mouse over to see what we're talking about. So here we're looking at items. And we're labeling it as an item here, that are either subcategories, subclasses of software systems, as we said, or instances of. So with this, I'm asking Wikidata to give me anything, all the concepts that ultimately are a subcategory of software system. And I'm returning it in the form of triples, of course, which is the way RDF is represented. And what I'm going to do is basically, let me run this query to show what it produces, because as you can see, it's form of triples, subject, predicate, objects, but we're getting these lists of entities. This Q72237 is a category, which is Cloud Big Table, right? We're getting the name, we're getting what's its parent category and its type. And like this, with all the triples combined, we're going to be forming a graph. But you don't need to care about that, because the result of this Sparkle query will be ingested directly into Neo4j using Neo-Semantics. So remember, this Sparkle query, we're going to pass it as a parameter when we do the RDF import. So we're going to show that in the next step. But before we do the actual import, and in order to show you the full step-by-step process, because we're literally starting from an empty graph, so I call it connections, and it's completely empty. So before you start using Neo-Semantics, you have to create a constraint, on the labeled resource and for property URI, and that's basically to store all unique identifiers. In RDF, everything is uniquely identified by a URI, and the way to store it efficiently in Neo4j is by creating, an index, a constraint that guarantees both the uniqueness, but also gives us, a fast access to it. So if I run this, I create the constraint, and then additionally, as you can see, what I'm doing is I'm telling Neo-Semantics how to deal with RDF, how to deal with the RDF that's going to be imported. In the previous step in the guide, you saw I'm probably going to click on the link just to show, but you have a link that will take you to the homepage of Neo-Semantics, and here you can take a look at the documentation and again see all the many different options. So I won't, of course, go into all the details, but there's many possibilities in terms of how you import the data into Neo4j, and that's what you set up when you called initially the init method. So what I'm doing here with this map is that I want to be able to rename the way terms are identified in the original RDF when I persist them in Neo4j. And what I'm going to be doing is rename these complex names in Wikidata into something more humanly readable in Neo4j. So that's what we do in the first step. That's done. And then we can go ahead and do the actual import. So don't be scared by this large piece of text here, but this is just, as you can see, it's an HTTP request on the Sparkle endpoint that we were seeing a minute ago. And this is just the body of the Sparkle query, but it's HTTP encoded. That's why it's not readable, but it's essentially the query that I showed a minute ago. And all we're doing here is we're calling the RDF import method in Neosemantics in NSNS, and we're passing the request and the format, the serialization format that's being returned by the endpoint. So if we run that, and there's no problem, hopefully it will take just a few seconds to download and import, in this case, 1600 triples. So that's the first kind of taxonomy that we're importing, which is about software systems. But we're going to run two more, and we'll look at the results in a second. So the second one is about programming languages. So we're going to run a similar query that will take the concept of programming languages in Wikidata and get all the concepts, all the entities that derive from it. And this has imported 9,000 and something triples, all done pretty quickly. Like I say, you don't need to worry about how the import, I mean, you can control it with some configuration parameters, but Neosemantics will do it for you. There you go. So we have imported the three taxonomies. The third one is about data formats. And now we can have a look at what we've imported. So this query will show us one portion of the taxonomy focused starting on version control systems, right? So one of the software elements of software systems that we've imported is version control systems. So if we run this query, we see that in Neo4j we have now a category representing version control systems with a number of subcategories under it, distributed ones, the centralized ones, and then we will have subcategories of each other. So it's a proper taxonomy. It's not necessarily a tree, because we see that there are some nodes that have multiple parents, but that's a replica of how the data, how this taxonomy, this ontology is organized, is represented in Wikidata. So yeah, we have run step one, which is the importing of the kind of structured knowledge. We can do a bit more, advanced exploration of your data. For example, we can take a category, for example, Neo4j, and explore all the elements that Neo4j is a subcategory of, all the way to the root until we have no other parents, and then we try to find some siblings, and that will give us another tree, but this time based in Neo4j. So we see that Neo4j is a subcategory both of free software and also of proprietary software. That's the way it's characterized in Wikidata. We can expand it, and I believe there's another one, it's a graph database, of course. And if we keep expanding, we see that there are subcategories of graph database, and on and on. But that's probably enough to do a little bit of exploration on the data, on the structured data, on the taxonomy that we've imported from Wikidata. So we'll get back to that. And now Mark is going to talk us about the importing of the fact.
Yeah. So now we're gonna have a look at the fact side of the graph. So we're gonna be importing some articles from this website called Dev2. So yeah, we just open that up there. So if you've not seen it, this is a developer blogging type platform, I guess. So if we scroll through, you can kind of see people write all sorts of things. There's a topic on CSS at the top there. There's some stuff about GitHub, some trending topics on GitHub. There's lots of articles on JavaScript and React. There's some stuff on Java. There's lots of stuff on databases. And so these are like the facts or the articles around the taxonomies that Jesus showed us how to import from Wikidata. And so what we're going to do is we've gone through there and we've picked about 30 articles from here, and then we've got them in this CSV file that Jesus has got on the screen here. So we can see we've just got a bunch of URIs, which are representing different articles for the topics in our various taxonomies. And what we're going to do is we're going to import. First, we're going to go and scrape those, put them in Neo4j, and then we're going to connect them to the taxonomy. So if we just run this query, and then we can quickly talk through how it works. So so if we start on line 2, we're just querying that CSV file of articles. Then come down to line 4. We're making sure that we've got a node with an article label for each one. And then from line 6 down to line 10, this is a web scraping. So it's got an APOC load HTML, allows you to go and scrape a web page. So we're pulling out the body. So that's like the CSS selector for where the body is. We get the title and we get the time. And then on lines 13 to 16, we're kind of just pulling the data together into a body, a title, and a date. And then finally on line 17, we save it into the node that we created on line 4. And then we're doing it, so line 18, we're doing it on batches of 5 items at a time. And so you can see on the results, we've got, if you look on the batch column, we've got 7 batches, 32 committed operations. So there were 32 articles we've done, and we've done them in 7 batches, and it's taken just under 10 seconds. And so if we go to our next slide now, we should be able to see those articles in Neo4j. So cool, so there we go. So you see, actually now we've got the PhoneGap article at the top, and you can see the URI was from the CSV file. The title's been scraped from the page, and the date's also been scraped from the page. And we could pull in other data if we want, like there's an author on the page, and there's probably some other information as well. But for the purpose of this demonstration, we only really need the body. The title is purely just for us to be able to understand what each article's about. Okay, so we've loaded in, so we've kind of got 2 disjoint graphs at the moment, right? We've got all these articles on one side, and then we've got the taxonomy that Jesus showed us how to import the other side. But there's no connection between them at the moment. And so that's where the NLP piece sits. So if we just open this link, so this is a link to the APOC NLP for GCP documentation. So you can see here, it just explains what procedures are available, how exactly they work, how you configure it with your, how you set up like credentials to have it work with your Google account, and then it has a few usage examples at the bottom of the page. We're going to be using the entity extraction procedures. So yeah, you can see on the screen there. There are two different ones. We can either get back a stream of values, or we can actually get it to create the graph for us. Since we're going to be doing something a little bit custom, we're going to use the stream version. And I guess if we can go back to the browser again, we can show what that query is going to look like. But first, we need to put in our key. So we need to put in our GCP key here. So you need to set up a service key that has access to the natural language API. We'll be expiring that one after we're done. And then we can run it. So I guess we'll run that, and then we'll just talk through it. So if we expand the query now, so again we're using APOC periodic iterate. I guess we didn't point that out on the previous query. So this is again allows us to batch the calls for each article. Otherwise we'd be doing one article at a time. And so we're batching them into batches of 10. Send it to the procedure on line 5. And then it's reading the body property. So you can see that on line 6. It's using that as the text. And then this comes back with a stream of lots of different entities. So there'll probably be like between 50 and 200 for this size of article. But we're not really interested in most of those. We only care about the ones that are in our taxonomy. And so that's what line 14 is doing. So the GCP API is quite cool because it gives us back a Wikipedia URL. And so we can actually go, okay, let's only return the entities that have a Wikipedia URL. And then on line 15, we're going to connect that into our graph. So if there's already a resource with this URL, we'll connect to that, we'll return that. And if otherwise we'll create a new one. And then we're also adding a Wikipedia page label on line 16. And then finally on line 17, we're connecting the node where the node is the article to the entity that we just pulled out. So we just have a look. That should probably have completed by now. So you see that's taken about just over 30 seconds. Again, we've done 32 committed operations. This time we did it in batches of size 10, wasn't it? Yeah, so we've got 4 batches. So now I guess we can go and have a look at what how we've enriched the article part of the graph, and actually how we can search it. So I'm going to hand back to Jesus now.
Cool, excellent, thank you. Yeah, so well now, like Mark just said, we have our taxonomy, our ontology connected to our data set, our set of articles through these set of terms or set of concepts that have been extracted through the NLP process. So what we're going to do is now show how we can easily do this idea of a semantic search. So let's say we're interested in a particular category. So we're interested in documents about NoSQL, right? NoSQL database management system is the complete term in Wikidata. And what we're doing with this method in NNS is that we are getting all the subcategories of this category that we have selected down to the leaves of the tree, if you want. So it will go as many levels deep as needed. And for each one of them, we'll try to find if we have any article attached to it, right? So essentially what we're returning is all the articles that are directly or indirectly tagged or related to NoSQL database management systems. So if I run the query, what we see is that it's returning as a list. And what we've added in the last column is what are the explicit topics that the NLP process has extracted of that document, so of that article. So in this case, it's fine. The first one, would have been a match anyway, because it's explicitly about NoSQL. But look at the second one. The second one is about Apache Zookeeper, right? So this is, effectively a technology that's related to one specific NoSQL technology. But it's not explicitly labeled as NoSQL. But by exploring this explicit knowledge, this taxonomy in our case, we're able to understand that the notion of NoSQL includes some other more specific categories. So that's what we've done. So we've kind of transformed a syntactic, if you want, query into a semantic one by expanding it, taking into account this taxonomy of categories. And same with many of the rest that you can see here. So you see that there's articles on Redis or articles on MongoDB and many other technologies that are not explicitly related to NoSQL, but still are relevant results for our query. So that's the first example of how we can exploit the model that we built. Another one is we mentioned this idea of computing concept similarity, right? And we can show that by, for example, taking an article and finding others that are related to it. So the most simple approach to do this is find articles that share the same topics, the same concepts, right? So that's a simple path that we're expanding here. So we start from an article, and this one is about performance testing of Neo4j. That's the URL to identify it. But then we find for this article, we find the entities that it mentions and the concepts that identify them in the taxonomy, and then we find other categories that are in the same other articles, that are in the same category. So that's a pretty simple exploration, but we can see that the performance article is connected to Neo4j, and we have two more articles about Neo4j. That's fine, but I would say that's pretty simple, right? In the sense that we're just finding articles with the same tag, with the same topic. Now, what we can do is we can expand that and explore the hierarchy deeper, or higher if you want. So we are, again, starting from the same article on performance testing in Neo4j, and we're going up the hierarchy. So we're identifying the categories that it talks about, but then from the categories, we're going to be exploring their parents and keep going up, to the level that we decide. And that's something that we can discuss a bit later, how we can tune that to make it still meaningful without being too noisy. And then once we get, for example, to the parent, we can expand to other subcategories and then get an additional level of similarity. And if we look at the results of this kind of query, well, we now see that there's a number of related articles to the one that we selected on Neo4j performance. And one thing that's extremely interesting of these kind of knowledge graphs is the explainability. So you can tell how you came up with this recommendation or with this similarity. And we know that this article on Postgres, is it Postgres and MySQL here? So we know that it's related to Neo4j because both are subcategories, at least in Wikidata, of proprietary software, right? So we see that Microsoft SQL Server appears as a proprietary software, so is Neo4j, therefore they are related. And same with PostgreSQL, right? So that's the how you can combine that to find these two elements to find similarities. Now you can say it's true that the taxonomy in Wikidata, well, in this sense, is not extremely interesting because the fact that they are both proprietary software or free software might not be super, I mean, it's relevant, but for this type of search, maybe not too much. So here's where we think that we can bring additional bits of explicit knowledge. I mean, we can have our own enterprise ontology, our own custom ontology. And that's exactly what I'm going to show you in this next, I think I must have it somewhere here. Here we go. So what we've done is we've developed an OWL ontology. OWL, for those of you who are not familiar, is kind of the standard W3C vocabulary for defining ontologies. It's also based in RDF. And we've created a simple ontology on software stack. So we're defined here, we've defined the grand stack, which is composed of, as you all know, of GraphQL, React, Neo4j, and Apollo, and some others like the mean stack, which is Express.js, MongoDB, Angular, and Node.js, the LAMP stack, and some others. So even if you're not super familiar with RDF and OWL, it's pretty straightforward to see that we're defining a category here, a class, which is grand stack. And we specify that it's a subcategory of software stack, and they all have a label, a human readable name, and then we connect the others to that category, to that class. And you will notice that we're using common terms, standard terms. So we're using the Wikidata terminology. So, for example, to refer to GraphQL, we're using the GraphQL unique identifier of Wikidata, and that way, it's going to link together nicely when we import it into Neo4j. So that's the whole idea of RDF. So RDF, it's all about interoperability. So it's based on this idea of, well, of course, presenting the data as triples, as a graph, but also identifying things in a unique manner to enable things linking together nicely. So that's what we are achieving with this. So we have our own custom ontology. This is on software stacks. So we can easily imported into Neo4j, pretty much in the same way we did with the data from Wikidata, but we have to add a couple of additional transformations or mappings if we want. So we said that we're using the OWL language. It combines elements from OWL and RDFS. So I'm defining the two prefixes and defining aliases for the standard terms in the OWL and RDFS schema languages. So that's what I'm doing. Every time in a standard ontology, I use the notion of subclass of, which is something you saw here, which is a standard RDFS OWL term. So I will want to persist it in Neo4j with the more nicely readable subcategory of. Same with the label, I'm calling it name, and same with the class, I'm calling it category. So I add these additional bits of configuration, and once I've done it, I can import my ontology by just calling the NTNS RDF preview. Preview actually will not import it, will just show me what it looks like, will give me a graph-based preview of it, and then we'll run the input. And I just need to point at the URL that I showed a minute ago, where the actual ontology lives. So if I run a preview, it's going to show me in Neo4j what it looks like once imported as a property graph. So you see the three software stacks that we saw in the document. So the LAMP stack, the grand stack, and the mean stack, and each one of them with their related technologies. So we like what we see. That's exactly the graph that we want to build. We see that the names of the relationship have been converted, have been mapped, so all good. And if we're happy with that, then all we need to do is replace the preview with the import, and it will effectively persist that in Neo4j. So all 58 triples in my ontology have been imported, and now we kind of have overlaid together the taxonomies from Wikidata with my own ontology. If I get rid of this, I can go back to the previous query that I showed when I was trying to get similar documents, recommendations for our article on performance testing in Neo4j. And if I run it now, you're going to notice quickly that we're getting some additional and probably more interesting results. Same query, and that's the interesting thing. So it's exactly the same query. Now it's returning additional results because we have added some bits of explicit knowledge, some additional taxonomy elements. And we see that now we're getting recommended articles on GraphQL. Interesting. Why is that? So we can look at the explanation part, and we see that both GraphQL and Neo4j are related because they're both part of the grand stack. So I think we can see how powerful this combination of bits of explicit knowledge with actual data can be because it will enable you to combine, like we've seen, public taxonomies, ontologies with your own one. I don't know if you wanted to add anything else, Mark, or I think that's pretty much all we wanted to show in the demo. So
yeah, I guess we can go to the questions now.
Probably. Cool. So let me get back to the deck and see our faces, and maybe we can check if we have questions from the attendees.
Yeah, definitely. Hi guys, this is Greta. Great presentation. Thanks so much for joining today. We have tons of questions already coming in, but just to remind the audience out there, go ahead and type them into the Q&A portion of your big market control panel. And if we don't get to them today, someone will follow up with the answer, or might answer in the chat itself. But we've got a ton, so let's go ahead and get to these guys. Can I import JSON LD with N10s?
Yeah, I'll take that one. That's a yes. That's a quick one. So JSON LD, for those of you who are not familiar with it, is one of the possible serializations of RDF. So it's actually graph data, is RDF data, but it's serialized as JSON, and it's pretty popular these days because it's one of the formats that is being used a lot by websites, including metadata in the web pages, so that, for example, the Google Knowledge Graph can extract it and make it part of it. So that's why it's being very popular. But like I say, it's just another serialization of RDF, so it's absolutely possible. You might have noticed during the demo that when you import RDF with N10s, we're calling it, I mean, we have to explain why we're calling it N10s. That's a pretty cool reading of the acronym. We came up with N10s as a short for neosemantics, but then Dave Allen said that's a great name. It's N10, so we're now using the two. But yeah, we're all talking about the same. It's all neosemantics. So what you call this method in N10s, you have to pass the serialization format as a second argument. So in this case, you would just put JSON LD, and it would just do exactly like what we did in the examples today.
Okay, cool. And what other NLP options or techniques are available in APOC?
Yeah, so one for me. So yeah, so we looked at just one of the things that we've got there. So we basically wrapped the whole natural language processing APIs for Azure, AWS, and Google. So basically got one procedure mapping to each of those. So for Google, we have entity extraction. They also have a category API, so they give you back like a category. It's a little bit similar to the Wikidata one that we looked at in the presentation, but we felt it was kind of too generic, so it wasn't actually giving us so interesting to query as the Wikidata one. You can also do sentiment analysis. I think AWS and Azure both pull apart entities and key phrases, so they kind of treat them as separate things. And then they both have sentiment analysis. So you can go, here's a piece of text, tell me if it's positive or negative. But yeah, if there are obviously other APIs. If you see anything else that you wish was in the library, you can let us know on the community side. I guess that's probably a good place if you have any questions afterwards. So it's community.neo4j.com.
Cool. What types of inference can you do with N10s?
Right, I'll take that one. We showed just a basic example of inferencing, which was based on on basically expanding transitively the subclass of a taxonomy. So that's one of the things that you can do. We've never tried to. I don't think it's. Might be wrong, but my approach has been more pragmatic, and what I mean is I haven't tried to build a general purpose inferencing engine. So the inferencing capabilities is limited in the traditional understanding of general purpose inferencing engines. There are some partner products out there that can do more sophisticated inferencing in the traditional way, but we focus on more targeted ones like these, which is relevant for things like recommendation and semantic expansion of queries. But there's one element that N10s includes, which can be grouped together with the inferencing capabilities, which is the constraint validation. So one of the languages, one of the standard languages that the W3C curates as well as OWL, which we talked about today, is Shackle. And Shackle is, they call it a shapes language, which is a way of formally expressing constraints on your graph. So you can say things like, I want the cardinality of this relationship to be this or that, and many more. You can say the domain or the range of this relationship has to be this type of nodes. And then use that to detect inconsistencies, so to detect violations of these constraints. So this is something that Intens does right now. And I would say it's also part of this kind of more inference-oriented use of it. So I think that's what we can say.
Okay, very cool. And then we had a couple questions around scale. So can you talk about some techniques, or how do these techniques scale to millions of entities?
Yeah, so shall I do the NLP side and then you do the other?
Yeah.
So yeah, the NLP APIs for each of the cloud providers have kind of different approaches to this. So the Google one only allows you to do one text document per API call to their API. They used to have a batch API, which is now deprecated, so we can't use that. But we do batch it inside the procedure. But obviously, there's a HTTP call there, so it's not like a thing that you could run in a real time. This would be more like a thing that you're running in the background in a batch type of job. The Azure and AWS ones, I think they allow you to do batches of 25 items. Obviously, you could, if we're doing big amounts of documents, you have a lot less HTTP calls to do that. And I guess for the Wikidata, it would be pretty similar, I imagine, Jesus.
Yeah, I guess the problem of scale can be on the taxonomies. It can be looked at from two angles. So one, let's say you're bringing a massive, let's say, taxonomy or a massive ontology, and there are some out there that are pretty big. Like I can think now. I think I mentioned it in the documentation of Intens, which is the NCB taxonomy, which is basically it's one of these natural science ontology that contains everything in the world. And it's literally millions of entities. So you can import that. I mean, I wouldn't recommend doing that over HTTP and streaming it from a server like we've done with Wikipedia or Wikidata for this example. But you can download it and import it, and that you can do. So that's absolutely fine. And then in terms of inferencing, as we've shown it today, that's something that you will get relatively good performance. So you can traverse. Keep in mind that we're leveraging one of the basic capabilities of Neo4j, which is our native nature. So we persist every connection in a hierarchy. It's all the subclass of. So being able to expand them and to traverse them very quickly to find matches is something that we do quite efficiently. So I don't know. I can say that I've tested it with pretty large ontologies, large as I found, and performance was reasonable. There's one thing, and I'm going to extend the question probably for you as well, Mark, because I was talking to the team this earlier today, and they mentioned, but would you always want to, for example, save in the node the whole content of the article? And I would say, well, in this case, we used the whole text. Maybe sometimes you want to bring the abstract. Maybe sometimes you may not even want to persist it. I mean, is it possible maybe that you want to, I don't know, can you, for example, would it be possible to chain the result of the entity extract, I mean, from the scraping with the entity extraction with the NLP, as a way to prevent you from saving all the text? I'm thinking just...
Yeah, I mean, so at the moment, the way it's written, it assumes that you're passing it a node. But I guess what you could do is you could create like a fake node. Like you could create a virtual node using APOC, and you could say, hey, here's a virtual node with some text, and have it process that, and then you don't necessarily store the raw text anywhere. So yeah, I think that would probably be the way to do it. Right. But yeah, I mean, yeah, if it could be that we need to change that API so that you can just say, here's some text, give me the entities as well.
Sorry, Greta, we've made this more a conversation than an answer, but I think we kind of covered a little bit there. Yeah,
that was great. Okay, and how do you deal with dense nodes in taxonomies? Kind of like, I think you showed a free software example that had a pretty dense node.
Yeah, that's I guess we can both add to that. I mean, the idea is that like we saw before. I mean, if you explore, let's say you have a taxonomy, and in the example of Wikidata, we had all subcategories of, was it software system, right? There were like 3 or 4 top levels: software system, data type, or was it? I can't remember.
Yeah, we did data formats as well. Data
format, exactly. Yeah. So if you keep going up in the hierarchy, at some point you're going to be having every article under that category. So it's true that I don't think there's a simple answer to that, but maybe you can add certain checks as you expand. For example, if you get to like you say, one of these dense nodes, for example, free software. Free software is a maybe not super meaningful category because it will contain all sorts of things. So maybe, I don't know, something like adding a limit when a category has more than N, and you give a threshold. Let's say if it has more than 10 subcategories, then it's not that meaningful for recommendation, and it's basically noise, so we can skip it. Something like that, right? And similarly, determine how far or how high you want to go in the hierarchy. But I think this is more on a case-by-case basis and on an experimental way. I don't know. That's the experience that what we saw when working with this data set. But I think that's kind of generally valid advice.
Very cool. So I think that's all the time that we have today. Just a reminder to attendees, if we didn't get to your question, someone will probably reach out with the answer. You can always email us at webinar@neotechnology.com. But I'll pass it back to Marilee. Thanks, Mark and Jesus.
Thank you. Thank you, Greta.
Hello. Thank you, Mark. Thank you, Jesus. And thank you, Greta, for the assist on Q&A. And just to clarify on that email address, it's webinar@neo4j.com. We'll get both, but it's a cleaner way to get to us with the neo4j.com instead of the Neotechnology. And also, I want the audience to know our next session will be starting in just a few minutes. So stick around and we'll get that going here shortly. And again, thank you, Jesus. Thank you, Mark.
Thank you.